Okay, folks, this is Todd Coburn with lecture 15 for ARO3271 at Cal Poly Pomona. Today we're going to cover welds, and what we're going to focus on is a simplified approach for calculating our torsional properties of a weld that will work for certain kinds of simplified or simple welds. So this slide here shows a number of different simple welds. For example, weld number 1 in the table is just a vertical weld, a single vertical weld. Weld number 2 is 2. We can call that the snake bite weld, since we have 2 vertical welds. We've got an L weld, a C weld, a box weld, and a round weld. And for each of these, if you find a weld that is precisely like one of these, we can use a simplified approach rather than constructing our table of weld properties like we did last lecture. In that case, we can see this table gives us what the weld area is and what the location of the CG of the weld is and what the torsional constant is. Now, one word of warning, the torsional constant shown in the table is not the full torsional constant. It actually is just a portion of it. So we can say we can call it the unit torsional stiffness, J sub U, and we will then need to multiply by the weld dimension 0.707H for fillet welds. For example, if we have a vertical weld, we see the area of that will be 0.707H times the length of the weld, which is called D here. The X bar is going to be at 0, the Y bar at D over 2, and J sub U is D cubed over 12, and the full J is 0.707HJU. Of course, this is assuming that that vertical weld is a fillet weld. If this vertical weld were actually like a butt weld, a through thickness butt weld, then instead of multiplying JU by 0.707H, we would multiply it by just H. If we get weld number 2, a snake bite weld, we can see the properties there, A, X bar, Y bar, and JU. If we have an L weld, you can see the same information. Now here, a word of caution is in order, because you'll notice that the X bar and the Y bar is identified in the actual figure. We can see it's located from the lower left corner of the weld, which is fine as long as we find precisely this weld. If we find a different weld, for example, upside down L or a sideways L, then that will change the reference point from which the X bar and Y bar computed in these equations will be referenced. So you're going to need to be sure, if you use this simplified approach for that kind of weld, to make sure you orient your sign convention and then you communicate clearly in your work about where you're taking that centroid from, and then when you use that centroid to calculate, for example, the properties, the moment on that weld, you'll need to make sure you're calculating it to the correct point. In the same way, the X bar and Y bar are located in figures 4 and 5 for the C and the box weld in a similar manner, and you need to take the same kind of precaution. Another word of caution is in order, and that's because these welds are given dimensions like B and D. And often, the problem statement will also identify dimensions, and sometimes it will use symbols like A, B, D, and other things, and H. Just because the figure you find on a problem statement or in somebody's sketch of a problem uses one nomenclature does not mean that same nomenclature applies to this particular table. When you try to use something from this table, you're going to need to first convert the nomenclature from what you find to what you need before you use the information. Much like you would have to if somebody speaks another language to you, and then you try and communicate what that person says, you're going to have to convert it to the language of communication for whoever you're talking to. So With that said, if we find one of these welds, we can use this approach in lieu of our other approach. Now you'll notice these welds, the J's for these welds, are neglecting that small term, the 0.707 h³ term that we talked about last time. So if you compare this, these numbers to numbers you compute using the other method, and if you aren't neglecting those terms when you do a more detailed analysis, your numbers will be slightly different. And the stresses computed using these formulas will be slightly conservative or larger than they actually are. Having calculated the J's for a simple in-plane loaded weld, our calculations for stress will be done in the same manner. We're going to get an X component of stress, a Y component of stress, and a resultant stress. One more word of caution is in order, and that's that these are all for a weld loaded in plane. What that means is that the weld is all in the same plane, as you can see, and any forces and moments also lie in the exact same plane, or else, or a better way to say that is that they cause stresses in the same plane, which means your forces actually lie in the plane and your moment is actually perpendicular to this plane. If all of that is true, you have an in-plane planar weld, 2D weld, and you can use this approach. Now, if we find a weld of the same type, or one of these types, and it's loaded with an out-of-plane, which means that our moment lies in the plane such that it causes stresses out of the plane. If that's true, then we're going to use this table to calculate the I sub u. Once again, that's the unit moment of inertia. And we will convert that unit moment of inertia to the actual moment of inertia by multiplying by 0.707 h. What this means is that this simplified approach can be used if one of these welds applies. The same cautionary notes apply, such that the X bar and the Y bar are located from specific points on these welds, and you need to convert anything you find into what this table shows prior to using the information you calculate. When we come across one of these welds loaded out of plane, we will find that the same principle applies and our stresses are calculated in the same manner as before. Another cautionary comment about this simplified weld and the previous in-plane simplified weld procedure is that both of these assume that all welds have the same H dimension. If all welds do not have the same dimension, then this method cannot be used. You will need to calculate the properties in the more detailed way that we said last class. Also, the same caution about the weld applies that we said last time, in that if this is all fillet welds, this 0.707 h times IU applies, but if any of the welds are butt welds, if all of the welds are butt welds, then the I is simply h times IU, and if some of them are fillet welds and some of them are butt welds, then you'll have to use the more detailed procedure in order to get a precisely correct value. Got it? Okay. Let's move on to the strength of welds. So if we look at the strength of welds, we actually are going to have to concern ourselves with a few things. We're trying to fuse these materials together, and what we're going to need to look at is both the tensile strength in some cases and the shear strength of the weld. We're also going to see a knockdown in properties in the base material that we will also have to watch out for. Okay? And that's basically what this slide says. Let's go to the next slide. And what this is showing is the strength of fusion welded joints for steels. And this shows typical shear and tensile values. And it shows some other information about it. This is really for your reference. We're actually not going to use this slide. This is providing information about welding aluminums, and we're not going to focus on this either. This is for your reading and learning pleasure. And what this is saying is this is showing the relative weldability of various aluminums. What this code means is if you see an A here, it means that the material is pretty much weldable, like a 2219 or a 2124, neither of which I have worked with much in my career. Now if we move on down, 5052 is occasionally run into in strength applications. You can see that's very weldable. And if we go down to 6061, the pansy material that a lot of electricals use for their brackets, that's pretty weldable. But when you get down to the more common structural materials like a 7075, we find it's only C, which means it has limited weldability. Now that doesn't mean you can't weld it, because I've actually seen some parts that are welded that way. But it means you probably should avoid it, because it may not give you the properties you think it's giving you. In the same way, 2024, another very common structural application, is not very weldable. So just to be aware of this table and these generalities. This brings us to weld electrode strength. So like I said, there's going to be a couple things we're going to look at. We're going to look at the strength of the electrode and the strength of the base metal. And both of these have potential to fail when the weld is loaded. If we have an electrode, we find from this table that electrodes are classified roughly by their tensile strength, and they're giving a designation E something, like E60, E70, E80. What that means is an E60 electrode has roughly a 60 KSI allowable tensile strength. Now if you look at the table, you find it's actually not 60 KSI at all, it's actually 62 KSI. So the first thing we're going to do if we have a weld is we're going to look at the electrode strength. If the weld is loaded in tension, we talked last time about loaded welds and whether they're in tension or shear. If they are loaded in tension, we will use this tensile strength, the first column of this table, for the ultimate strength of the weld. And you'll see also we have the yield strength for those welds. If we need the shear strength of the weld, if you look down below, you've got 3 horizontal rows, and the second one is actually the shear strength. So we see that a E60 electrode has a 18 KSI shear strength. E70 electrode has a 21 KSI shear strength, and so on. So for the electrode, this is where we're going to get the strengths. We're going to get it from either the upper table for the tension strengths and the lower table for the shear strengths. We're not going to use the line strengths at all that are provided here. And over to the right, we have some very difficult to read SI allowables for the same. Okay, we're not going to use those either. Now, when we start looking at the base metal, what the AISC code for welding says is that for different types of welds, we have different permissible stresses. These already have factors of safety buried in them. And generally, if we weld, we're going to use these kind of values. So what we're going to do to make this table rather simple is, if we have tension on a weld, we will use 60% of the yield strength. If we have shear on a weld, we will take the minimum of 30% of the weld tensile strength or 40% of the yield strength. We're going to use this approach for both the base metal. So if we look up a weld, we can look up its FTU and its FTY. We can plug into this equation, and that will give us the tensile and shear strength for the weld that we will use. So here's our basic approach. We're going to get the strength of the electrode and the base metal. We're going to check if there's a reduction in strength of the base metal due to potential loss of heat treat. What that means is, if the problem statement says that there is a loss to the base metal strength, say of 85%, a 15% knockdown in strength, or a 20% knockdown in strength, or a 10% knockdown in strength. What we will do first is take the FTU, FTY of the material, knock it down by that number, and then apply this formula. We're going to use 60% of the yield strength for our tension allowable. We'll use the minimum of 30% the tensile ultimate and 40% of the yield. And whichever one dominates, we will write our margins of safety against that. If we state in the problem statement a different approach, we'll use that, but generally this is going to be our general approach. Make sense? All right, let's move to the next slide, which basically is practice. So we're going to look at some of the problems that we practiced on last time. The first one is here. Last time we looked at this, we saw this problem, and you guys told me that this was a 2D weld loaded in plane, and that's true. We can use the method from last time where we put in the properties of each weld and calculate the properties of the weld pattern. But if you look at this, you also notice that this L weld applies to the simplified procedure, and we can use the simplified procedure for in-plane loaded welds for this problem. Okay, here's another one. This one, if we look at this, we can use the approach from last time to solve, or we can also use our simplified box weld approach. We saw that this force, while the force is in plane, it causes a moment that's in plane, which means it gives out of plane components. So this uses the out of plane approach. We're going to calculate the I of the weld and solve it that way. And these are the component reactions, and we saw these last time. Weld. Let's say we have a problem like this. This looks like a snake bite weld, but actually it's loaded even more simply than that. Since the load goes through the center of the fastener pattern, we can just take that force, divide by 2, and divide by the area to get our stress in the weld, and that would be a shear stress. This here looks like what we have is a C weld. We actually have 2 C welds on top of each other. We can actually just calculate the JU and the J of one of these, and then multiply it by 2 to get the J of the entire pattern, and then move our loading to the centroid and analyze it that way. This one looks like a snake bite weld loaded out of plane. So we'd calculate IU, and then we'd calculate the moment at the centroid of this, and then analyze the weld for the stresses. Here is a little problem. If we look at this, we see we've got a back-to-back fillet weld, and what that says is the way that's shown, it's shown that the upper surface and the lower surface have the weld. So it's along the upper B dimension and the lower B dimension. This looks like the 2 horizontal welds. This is loaded out of plane, and therefore we calculate. We can either use our detailed approach or our simplified approach to solve this problem. Here is using the simplified approach. We get our IU, turn it into an I, calculate our stresses. The stress calculations shown here are following Shigley's approach, where he has you calculate a tau prime for the P over A portion and a tau double prime for the MC over I portion. And this is a little sloppy. I'm following it because I'm copying Shigley's example here, but the approach that I gave you is more certain to give you appropriate results every time. I recommend using that approach. If we use our more general approach, we would construct our table of properties for all these things using these equations. Here is a different weld. Here we have an all-around weld for this flat bar, which means we basically have a box weld. We can analyze it by doing the detailed weld procedure we saw last time, or we can use this as a box weld loaded in plane, calculate the JU, turn that into a J, and then analyze for the stresses. This weld looks like we have this indicator says we've got 2 fillet welds. They're back to back, but they're along the vertical dimension of the plate, the 2 sides of the plate. What this is a snake bite weld loaded out of plane. We can use the simplified snake bite procedure, or we can utilize our detailed approach as shown here. This one, once again, same thing. We have a snake bite weld loaded out of plane, and this is a three-dimensional analysis of this two-dimensional weld, and it shows the same stresses. Our last, this is actually the stress calculations for the last problem. And that's all we've got. That's how you analyze welds using the simplified procedure. Once again, we covered the simplified procedure for analyzing welds, and we covered how to evaluate the strength of the welds. That one slide is the key, where we're going to basically get the tensile strength, the yield strength, and multiply by the appropriate factors, take the minimum of those to evaluate our welds. Enjoy, Merry Christmas, hasta luego, signing off.